Good morning. My name is Pizarro. I'm here to present quantum snake oil. What ailments can it cure? I currently work for the European Space Agency, and let's get into it. Okay, first a disclaimer. This presentation only uses information from public sources, and as such is not subject to the implementation of the Western Agreement. Also, cryptographers, keep in mind, I am not a cryptographer, and I do not play one on TV. Okay, so what we've presented. So basically, I'm going to show you a little bit of quantum everything, a little bit of a primer on quantum, how maybe we're using quantum communications, and what are we in Europe at the European Space Agency using and quantum. So what are we doing? Well, you hear a lot about quantum. Quantum solves this, quantum solves that, quantum make you coffee, quantum will cure everything for you. But what do we really use as snake oil? What are we really planning to do in space with quantum?
Set course for Epsilon and engage quantum drive.
Course set, drive engaged.
I wish. Yeah, we're not quite yet using quantum drive yet, but reality, in Europe, we are planning a lot of quantum activities. So what are the maybe promises that quantum can resolve? There's quantum communications, there's quantum internet, there's also quantum computing. So, and we also have a small discussion about quantum key distribution. This is the one that the cryptographers really need to look at by disclaimer again. Okay, just before we get into it, let's get into a bit of primer. Quantum, most of us remember quantum physics at school. It was difficult, it was hard. Let's see if we can make it a little bit simpler to understand and have some, like, well, I don't know, kindergarten type level of discussion. Qubits. What's a qubit? Well, the fundamental unit of quantum is, well, it's like a normal bit in a computer, a 0 and 1, except it's really a 0 and 1 over a value probability sphere, what's called a block sphere. If you notice, the value 0 is the northern hemisphere and the value 1 is the southern hemisphere, a point on any surface. Okay, qubit states are represented either by what's called kets, as in like brackets, and it's a combination. It can be either 0, as on the left-hand side, or a 1 on the right-hand side, or a combination, which is called superpositions. These are the fundamental building blocks of any quantum activity. So, you've heard of entanglement. I mean, this is something that we've all heard about, but let's give maybe a simple back of the envelope type style thing get an idea how, not necessarily how it works, but how it could proceed. So, ready for the world's most magic trick. Let's take 2 cards, ace of coins, ace of clubs, and well, shall we? So shuffle. Oh, sorry, I meant entangle. Sorry, this is a quantum discussion, not a card show. So we entangle the 2 qubits. Then we'll send. We'll send one to Mars and put the other one in another envelope, send it to Earth. Okay, so that's we've prepared the state of both our qubits, and we sent 1 qubit to Mars, another qubit to Earth. So these 2 qubits are entangled. So let's measure on Mars. Which is which? Let's measure the Mars one. We open the Mars qubit, so we perform a measurement on the qubit. It's the ace of coins. So by faster than light communication, black magic, I don't know what, can we possibly know what the value on Earth could be? Let's see. Of course we know the Earth value. It's a 2-card trick. It's not really that difficult, but it's the ace of clubs. So this gives you an idea of what a qubit entanglements looks like. Qubit entanglements are a little bit more complicated by this. You also add factor other dimensions, but this is just to give you a grasp. Okay, so you measure one entangled qubit and you deduce the properties of its partner. This means it could be either an either or it could be the same property. This is like the more complicated part of qubits. I'm not going to get more detail, but you've got a vague idea of how things work now. So, quantum computing. All right, so you've got qubits, we've got entanglement. What else is quantum computing? How does that work? Well, let's take another card trick, maybe to give us an idea of how things could possibly work. This was a little bit better than the last card trick. I assure you, it's got more cards. So, entanglement. Find the lady. I think you guys in the US call it Monty. So we take 4 cards. Our goal is to find a queen, let's say a red queen. Okay. Normally, when a human plays cards, it takes between 2 1/4 turns on average to be able to find by turning the cards to find the right card. This has been explained a little bit better by Dario Gil in IBM Research. Okay, so I couldn't bring a quantum computer. Let's do it a different way. Let's ask my friend Vadim to do something. So we have our 4 qubits. And we're looking for the red queen, which is the queen of diamonds. Thank you, Adam. So we take the 4 qubits. Let's now, come on, Vadim. We need to entangle these qubits. See, you start entangling the first 3, yeah. 1, 2, 3. And then we take our queen and we entangle all the 4 qubits together. Okay, and by using an algorithm called Grover's search algorithm on a quantum computer with these 4 qubits, we will find immediately the queen of diamonds. So that's all right. Yes, it's not magic, the real thing, but if you're doing a simple search and each of the qubits have some sort of mathematical relationship with each other, using the entanglement and Grover's search algorithm, it can allow us to find each and every time in one move the actual queen of diamonds. Okay, let's move on. Thank you, Vadim. Okay, this is Grover's algorithm. Yep, that's why we use got Vadim to show you it, because this is what's called a quantum circuit, and in another time, in another place, we could explain to you in more detail how these circuits work. The other algorithm you've heard about, of course, is Shor's algorithm. This is a way using quantum computing to actually factor prime numbers. It allows us to do this in a quick thing because it's effectively taken what was thought to be a mathematically difficult problem with factorizing primes, but it was never provably a difficult problem. Shor's algorithm provided us a shortcut. So what can we use quantum computing for in space? Let's see. We're thinking we could use them for optimization problems, flight dynamics, orbits, multi-planet orbits, when you do 3-body problems type things, materials, optimizing materials and structures, machine learning, optimizing database searches, especially if we're cataloging and identifying events in telemetry, or if we're categorizing different types of Earth observation products. And the obvious one, solving numerically hard problems. An example would be factorization of primes and trying to work through the quantum threat. Okay, so as we discussed, we're currently investigating quantum computing opportunities for system engineering and space flight, process and observation, mission event analysis, multi-orbit optimization, scheduling, resource management, which is also an interesting problem. So bear in mind, quantum is not just a faster computer. Just because you're using a quantum computer does not mean you're doing all your calculations faster. It's a different way of attacking the problem. So we've all heard of this now. We've got quantum computing and we've heard quantum threats and quantum opportunities. So what exactly is the quantum threat? Well, quantum threat is all these broken security algorithms we possibly might have. But have you seen, like NIST, organizations like NIST are already studying different new algorithms that are not based on prime number factorization. Actually, we can still use advanced encryption standard 256. If we double up the key length, we still pretty much keeps our data secure for what we need. We can use something called QKD. We'll go later on, but remember, QKD, no matter what anybody tells you, especially snake oil salesmen, it is not post-quantum cryptography. And then there's something about using a combination of these two things called QCI. That's a new acronym, and we'll go into explaining the acronyms later. Okay, PQC, post-quantum cryptography. Okay, post-quantum cryptography, these are the main cheat sheets. You'll hear something called QKD. This is basically allows you to exchange keys in a secure manner as input to algorithms. AES-256 and greater is still okay for now. And if you want to keep the equivalent level of strength as you have now, just double your key length. And as I said before, NIST is investigating new crypto not based on primes. But in the last month or so, NIST have announced they've selected an algorithm called Crystal's Kyber to protect information over exchanged over networks. They've also selected for digital signatures 3 different algorithms called Crystal's Lithium, Falcon, and Sphinx. And currently there are 4 other algorithms they're still considering. Okay, quantum communications. Great. Quantum internet, what's that? Quantum internet is basically a way to optically connect different quantum computers. Think of it like distributed computing in our current thinking. It's to exchange qubits between any quantum processor. And by exchanging qubits, you could provide additional privacy on the information on those qubits. Still in research and development, Delft University or Technical University is very active in this field, and it's in development of the new quantum memory, and it's still a small number of nodes. So QKD, the famous snake oil that all cryptographers love. Okay, what do we have? So for quantum key distribution, that sounds really fun. As soon as if you put quantum and key in anything, it sounds really exciting. These are some little sketches of basically how it kind of works. On the bottom, you see the way we prepare the qubits from the light source by polarizing, and Bob receives the key. And on the right, you see how maybe we might use it for space systems. We'll go into more detail. So QKD. The challenge is, how do you share a key between Alice and Bob, the famous pair, without nasty little Eve listening and stealing the key? Okay, there's 2 methods to this. First, you remember the world's worst card trick? Well, we can use that for something called prepare and measure protocols. We prepare the qubit. Remember I said prepare the qubit, the value of the qubit, and if someone measures that qubit, someone else will know. So it can detect any eavesdropping because there's a noise threshold due to quantum interferency. And you also use other protocols like entanglement-based protocols, which both Alice and Bob would receive a qubit with the same value. Okay, so what is it? Well, we have something called a BB84 protocol and other variants that's in a combination of using a quantum channel and public classical authenticated channels. Alice and Bob can agree a key without Eve actually deducing what the key is. So from the original paper, this is what was presented in Bangalore in 1984. I'll present something a little bit more detail, but there's another card trick for this, but I don't have time for that. So what do? Alice prepares a qubit in a basis 0 or 1. Remember the qubit 0, 1? It is presented in a cross polarization or a diagonal polarization, so up or down. So Alice sends a qubit prepared. Bob measures it randomly on a measuring basis, so he could either select to measure it in a cross or diagonal polarization. And Alice doesn't know at that Bob doesn't know in which polarization Alice prepared the bit. So they get a lot of series of values: up, down, left, right, left, right, right. As you can see on the second one with Alice's random bit second random bit, they've sent a right polarization value, and Bob's measured a up diagonal value. Now, so Bob then goes to Alice saying, well, for each of these bits, I measured bit 1 cross, bit 2 diagonal, bit 3 diagonal, bit 4 diagonal, and Alice basically replies, yes, no, yes, no, yes, no. Notice Bob's only explaining in which basis they measured the other Alice's qubit, not saying which is the value. Alice Bob's agrees. Okay, by doing this, when the basis measurements aligns with Alice's and Bob's, that's that value of the bit that Bob then uses to make the key. Eve is listening to this, and if Eve had manipulated any of these qubits, Eve would have increased the noise level, causing Bob to reject the value of that key, of that particular key bit. So, how would we use QKD? Well, we share in the QKD system. We're sharing some keys, but we're just sharing keys. So Alice would then use the common key with Bob and place it in another encrypting system to be able to exchange the real ciphertext that they need to exchange. Warning. Remember, QKD does not protect data. It's only talking about exchanging the secure exchange of keys. And depending on the key rates, one-time pads might be possible. But like I said, depending on the key rate, that's a critical value you need to ask about any QKD system. What is the key rate? So, myths and facts. Great. Snake oil time. QKD will solve all crypto problems. No. It's a possible key sharing method. It's between two parties sharing a shared secret keying material that they already share a key. Okay, then, but QKD will have got a really good key. QKD will protect my data at rest. No, QKD is only about keys. Keys don't protect data. If you take a really good gold key and put it into a plastic lock, it doesn't make the plastic lock any better. Okay, QKD is useless. Maybe. Maybe not. It depends on the application. QKD in the space domain is a technology driver in terms of single photon detection, in terms of optical links. It may have some applications that we'll see further for us. In certain aspects, it can have applications in the real world. It is not. You will not be having QKD for your web browser to buy stuff from Amazon, though. Okay, why are we looking at this type of things? Well, space security is important for the networks. We're looking at distributed delay networks. We're looking at networks to the moon. We're looking at networks to Mars. We're looking at networks to deep space interplanetary missions. We're looking at networks, even trying to figure out how do networks look when we do asteroid mining in the past. Space optical communications might use QKD because of the distances involved, and that we have the optical communications links anyway. So, how do you hack this without winning a Nobel Prize for physics? Okay, so believe it or not, there are already hacking groups that exist that are hacking QKD systems. There's one gentleman named Vadim, who you see below, and what they do is basically take a laser, shoot it at the polarization rotator, burn it out without you realizing it, so that whatever qubit that Alice thinks they're preparing, it's always the same value. It's always the same value. It's always the same polarization. So effectively, Eve has basically intercepted and changed what Alice is preparing. So QKD in space, which is what we're all here for. We're in the Aerospace Village. So ESA's ambition is to prepare a role where space has a role in quantum internet. As we said before, it's a first step into maturing the technologies, and we're also working with European and Canadian know-how to access the markets. Okay, so QKD, we've got QKD on fiber and QKD in free space. So Which is better, space or fiber? Well, fiber has only really a range of 270 kilometers if you're pushing the quality of the glass. Whereas you can do a QKD link over 40,000 kilometers, one hop in space. But remember, we're still talking about detecting single photons. That's detecting a single photon at 40,000 kilometers. You decide which is better. So why do we even need QKD satellites? Well, for example, China's built a what's called a trusted node network over 2,000 kilometers with 32 trusted nodes. That's 32 man-in-the-middle attacks for the network. Whereas if we did a space link instead of the fiber link of the Chinese, we could probably reduce the number of trusted nodes and also jump over areas where we can't actually run fiber across. So what kind of orbits would you use for a QKD system? Okay, of course, there's three classical ones: the low Earth orbit, the medium Earth orbit, and the geostationary orbit, or geosynchronous. So with a geostationary or geos orbit, you could put a satellite in that position and exchange keys through the entanglement between the two limbs of the Earth. And with a MEO one, that separation becomes reduced because you're at a lower orbit. You could even do it in LEO, but then you're basically probably doing a key exchange over two parties that of a range about between 400 and 500 kilometers. What is being looked at a lot is what's called prepare and measure, where basically we prepare on the left-hand side in LEO. And so you do a shared key with the spacecraft and Alice. The spacecraft moves along, talks to Bob, shares another key, and XORs the key between spacecraft and Bob with Alice's key, and in that way gives to Bob Alice's key. Technologically, it's easier. Okay, but remember I talked about key rates and bit rates. We have a lot of impacts, especially that single photon trying to get through, well, one, the distance, and secondly, all the background noise in the atmospherics and that. So, optical ground stations. What kind of ground station would you need? Well, look at these. These are the kind of real terminals for QKD space systems, between 1 meter and maybe 2 meters, depending on where the how high the orbit of the spacecraft is. These aren't small things. You're not attaching these to the back of your mobile phone anytime soon. And also remember, the atmosphere also defines which frequency we can use for our photons to come through, because this is actually a transmission of where the atmosphere is actually blocking light from the sky. So, and you've got to remember, depending where you are, you have problems with clouds. Depending on on your height, if you have a MEO or a LEO satellite, the air mass that the photon has to go through could be greater if it's on a low on the horizon, or it could be quite short if it's straight above the target. And you have the problems of lighthouse planet Earth, with all the light pollutions and other type things like snow backscatter. So what do we do in Europe? Remember I mentioned that acronym QCI, Quantum Communications Infrastructure. In Europe, there's different processes. There's the Euro QCI and Lux QCI and other national programs. So in 2019, the European Commission, which is different to the ESA, two different organizations working together, declared to plan a cooperation framework for the Euro QCI to build a quantum communication infrastructure. Euro QCI is foreseen to be a system of systems. proposal to contribute to this system is what's called the Saga program, and as part of the Skylight framework. It supports member states developing quantum communication structure, developing use cases for QKD systems, developing and validating the required technologies. Remember the single photon detectors I discussed, understanding operational concept for what a QCI system would work, and demonstrating how you can integrate a space system with ground infrastructure. The main requirements we've seen so far in discussions in Europe is that users want high key rates. The geographical coverage. It's not just mainland Europe. Europe is actually a global entity. There are European locations all over the planet, especially if you look at things like French Terre d'Outre-mer. We have security requirements. This is the bit, the snake oil part, the bit that cryptographers don't like, trusted nodes. As engineers, we can do a lot of hand waving, but we really do have to take their concerns into account to protect these trusted nodes. We're discussing the number of terminals, how big the size are, and the suitability for, once we've got the infrastructure in place, what else can we use the QCI system for? So, as I said, EuroQCI is a system of systems. Supported by national QCI programs, which is also supported by industrial QCI initiatives. As we said, this is how we foresee the space part of the EuroQCI system to look like. This is what we envision from ESA. So each of the different national QCIs interconnect via space links. So, and this is actually Luxembourg's contribution to the QCI system. As you can see, it fits into one of these small circles on the right to the EuroQCI system. So you have a space-based QKD system to communicate to the other QCI partners and also to other Luxembourg interests. Within Luxembourg being a small country, we can use dedicated fiber or dark fiber as well to do the key exchanges. We can also use dedicated international links to countries to the left, which is like France, to the right was Germany. And this is another slide with permission from Luxembourg saying they're foreseeing to develop with cooperation with SES a low Earth orbit satellite-based QKD system using a BB84 prepare and measure protocol and using a QRNG quantum random number generator on board. So as we can see, the success criteria that Luxembourg views is that they build a reliable network where they can help secure data transactions using QCI provided keys. It also helps advance Luxembourg industry in terms of other technical innovation and supports research and development, space development areas, and integrates with other European programs. So, what's the current view in space? What's currently in space now with QKD? Well, as I said before, we have the ESA Skylight program, the Saga, which Skylight started in 2016, Saga started in 2019, and we're continually helping to develop and define what the space segment of the EuroQCI could look like. Currently, though, these are the missions I've already flown. Have you seen? China's flown two missions on spacecraft and one on a weather balloon. Germany and Canada have flown QKD missions on ISS, on the International Space Station. Germany's flown CubeSats. Austria and France have flown other satellites. Italy's done a reflection sat thing. Canada, Singapore, Japan. The list is endless. And even within the last month or so, in July, China launched another satellite called, pardon my pronunciation, Yinyan 1, which is a 100 kilogram spacecraft at low Earth orbit to help them develop the procedures and methods needed for their QKD systems. And these are a list of the activities we've been doing since 2009 for the last few years within ESA. Thank you very much for your attention, and I welcome any questions.